Welcome. Um, this is going to be a video on a topic, a paper that I recently read named Direct Preference Optimization, DPO. So the title of the paper is Direct Preference Optimization, Your Language Model is Secretly a Reward Model. This is a December 2023 paper. I recently read this on a flight, actually, May 2024, and I've been digesting basically and processing this paper until I think I understand it. At least the key insight of it I thought was very interesting, and so I thought I'd make a video of this paper. You can see, it's by Rafaelov, and one of the key people here is Christopher Manning, who is well known from Stanford University, natural language processing. This is a paper that relates to large language models, and in particular, reinforcement learning through human feedback. So what I plan to do with this shouldn't be a very long video, but I plan to just talk a little bit about the motivation of why this paper is very important. I think it's a really important paper. It stands to be seen the impact that this will have, but this could be a huge leap, quite possibly. If you want to think of it in terms of, we had a leap with transformers in 2017. Then we've got, BERTs and GPTs. That was a huge leap. Reinforcement learning through human feedbacks was added into that. That gave us a huge leap, which, has basically was one of the essential components to get something like ChatGPT to work. And now I believe this, and not just me, but a lot of people are starting to look at DPO and thinking that it could have, it could be an additional leap in that whole sequence. So it's a really interesting work. I'm not going to do any code today. I really just want to do this video on, the what DPO, why is it important, basically. I want to kind of stress that. So anyway, if you are looking for a library to use this kind of work, I highly recommend the Huggin Face TRL library. That stands for Transformers Reinforcement Learning. So basically, you can take something like a GPT-2. They have very nice Jupyter notebooks here. You can take a GPT-2 or something that's available on the GitHub hub, and then you can use their trainer for reinforcement learning through human feedbacks, and basically fine-tune this model with this TRL library to do some tasks. So for instance, you can take a GPT-2 and then you want to make it so that it writes stories that have more horror. So that, like, the text has more horror or less horror. So that's something that you can do with RLHF just by providing examples of text that has horror, and then using horror, not horror, I should say, and then using that text to train what is called a reward model. And then the reward model would be used to, fine-tune the GPT. So I'll talk a little bit about that as the background. But in essence, in the past, you would use something like this tool technique here called PPO, proximal policy optimization. And proximal policy optimization was the underlying algorithm, if you will, in the reinforcement learning that would help to fine-tune a GPT to be able to, provide better text. So the idea is that you're kind of like, nudging a GPT to now be better at answering questions by giving it questions and answers. And those questions and answers, when you give it a question when you give a prompt initially to a GPT, it's going to give you some text that's, kind of related to that. But if you want to make it so that it learns that given this type of format of a question, it should produce this type of answer, then you need to create a data set, right, of those pairs of questions to answers. And then usually humans will annotate these and will say, okay, this is a good question and answer. So we've got these pairs, and that's the key idea with reinforcement learning. The problem with that is that you can't really do, a human can only do so much of that, right? So one idea that has come about is that, we want to give feedback, but we want this feedback to be given by another neural network. So that's why now, if you think, there's a GPT that's being fine-tuned, large language model, and then there's also, it's going to learn, okay, I give a question, I'm giving a question, here's the answer. If we had a human in the loop, the human would have to look at the pair and say, okay, this is good. Then he gets another one and they'll say it's bad, or even better, you're given a question, the GPT generates 2 answers, and then the human will say, okay, this one is better than the other. So 1 and 0, something like that. But the human can't really do this for every iteration. So that's why what makes sense is that humans will do this for a while, create a data set, and then another neural network learns how to take a question and an answer, and basically based on the human feedbacks, it becomes like a classifier, and then it just says, okay, this is a good one, versus these are bad ones, right? So that's the idea. So you want to have, in the example that I gave, for instance, I mean, this is a way, one of the ways that you could do it is, since you have a question and 2 answers, right? So when you train the classifier, you're going to have question and answer and a 1 that trains the model to see that, okay, this is a better generated answer versus the one that is question and answer, but it had the 0. So it was, less than the best one. So of the 2 that the human evaluated. So it would learn that the second answer was not good. So it would give it, you learn a classifier that given 2 concatenated question and answer, it should issue basically a 1 or a 0. And that's, if you think about it, it's just a normal classifier. You're learning how to classify things, got it, text inputs, and then a 1 or a 0. But so that's the idea anyway, to create and I have a formal write-up of that I will go over in a sec, but that's the underlying idea. So that's how reinforcement learning through human feedbacks has worked. You have GPTs, and this has been applied to them, and it has been proven to work, but it's difficult. This has been proven challenging, especially like for those, if you go on Hugging Face and try these things out on your own, you'll see that it's not the easiest thing. And PPO has been the algorithm implemented in the TRL library. And so, yeah. So if you want to try it out, I strongly recommend that you go through this library. It's pretty good. Now, Hugging Face has now implemented DPO as one of the trainers, as you can probably see down here. And that's what I'm going to talk about today. What the paper on DPO, it's called Direct Preference Optimization. And that's, a really very interesting idea that really simplifies the problem. And so I really like that. And in short, what I can tell you is, what is so great about it? Well, before, as I just said, you have a GPT, that's one neural network, and then you had a reward model, that's another network, and you have to train 2 networks now, and then the reward model is extremely important for the GPT to learn, the other network. But DPO proposes basically that you no longer need 2 neural networks, the GPT and the reward model. This is the reward model, and you can just throw it away. And they found that you only need to train a neural network by changing some aspects of the loss function. And so that's really what I'm going to talk about that. So in essence, think about it. Before, 2 networks, and now just 1. That's cutting, think of it cutting like 50% of the difficulty, or if you want to think of it that way. And so it's really interesting. All right, so anyway, so I wanted to motivate that you can do these things on the Hugging Face library, and there's a lot of good examples there. But my goal is to talk about the paper. So as I said, direct preference optimization is this paper here, and I have my own write-up of this, from an upcoming work. And so I'll kind of go over the insight basically of why this is so important. Okay. All right. So anyway, that's the paper. Let's, I'm trying to keep this video short, so I'm just going to dive into this. So I have these notes here, and I'll describe them basically. But so I talked about reinforcement learning through human feedback, right? So we have to think about this idea currently. We have two neural networks. One is a GPT, like GPT-2, and then the other neural network is a reward model, a reward neural network, which is basically a classifier. It's going to get as input some text. It's going to be the question and the answer, prompt and answer. And it should, given those two concatenated things, produce a 1 or a 0, right? And it says 1, this is good, 0, this is bad. How do we make this into a reward function? Well, as we know in classifiers actually don't produce, a 1 or a 0. They actually produce a vector, let's say, of 2. And that vector, or it can be a 1. But it's basically a logit that's just going to be some kind of probability distribution, such as 0.05 to 0.95. So really, you just take one of those, and that 0.95 on being, a good answer, becomes a reward that is actually a real valued number, not just a discrete number, but, it could be 0.6, 0.7, 0.8, and it can be used as a reward function. So anyway, that's really an interesting thing. So let's go over a little bit. So remember that. So the whole point is, I have a GPT and a reward model, and this paper says that I can take out the reward model and I don't need it. So how did they do that? How did they figure that out? So the key is in the loss function, right? So the loss function currently requires to train a GPT to have a neural network that is a reward function. So their whole proposal here is that the loss function no longer needs to be in terms of any reward function, and they found a way for it to be all in terms of the GPT itself. And so that's what's really interesting about it. So as I've said, so I'll go over, as I said, these are my notes from an upcoming paper. So I'll just kind of read through some of the ideas here. In traditional RLHF, we need to train two neural networks, one for the RL policy and one for the reward model. So the RL policy, so that's policy just means, the thing that makes the decisions here. So we're talking about basically the GPT in this case. You can think of it that way. So the reward model is usually trained via human feedbacks, right? And then the neural network should, once it's trained, let's say it doesn't need all the data that a pre-trained LLM needs, so this can be 100,000 examples, for instance, as it can be very expensive to have human annotators. So RLHF tries to find the optimal reward model for use in training. As such, two networks are needed. So let's think about this simplistically. So simplistically, a reward model can be obtained from training a binary classifier. And like any classifier that you've ever used, think MNIST, you give it, or Iris even, you give it some feature vector of 784, and it produces a vector of 10, right? That kind of classifier is what can be used for a reward model. So the idea is, given a state, the policy selects two actions. So in this case, is basically like the GPT in this case gets an input, and then it's gonna, so these two actions is just the text that it generates. So given a question, it generates two answers. So in the notation, this will be written out as YW and YL given an X. All right, so X is going to be the prompt, and then these are the two answers that are provided. So these two sets of state action pairs, or prompt and question pairs, are labeled by a human as good or bad, and this label data is used to train the binary classifier, the reward model. So that hopefully should make a lot of sense. So in essence, you train a reward model, a neural network, and you also have a GPT model, and these two are going to work together through some loss function to basically train the GPT to be very good at that specific task. Once trained, this reward network can be used to optimize the policy network, the GPT. So as I said, this paper is for something else, but DPO presents a recent breakthrough in RL and research that could have a very high impact in many fields, such as large language models. So I'm referring, of course, to this paper, direct preference optimization. Your language model is secretly irrelevant. So anyway, I think that's enough of, like the background. Now let's get into DPO. As I said, I just have a short summary here of their paper and the key aspect that I thought was really interesting of what they did. So basically, direct preference optimization, DPO, is a groundworking methodology that I think can have a huge impact in RLHF. So I'm really I think everyone is really excited of, being able to create, better GPT models, that are just easier to train. Previous approaches have required a policy model and a reward model. So the two neural networks, right? DPO removes the need for a reward model, therefore simplifying the whole process. In their paper, the authors showed that DPO basically can fine-tune models, such as a GPT, using a simple classification loss. Okay, so that's, it's very interesting. Now, the whole point of it is that it was basically mathematical intuition. It's like whenever it's like whenever you did something in algebra where you had like x equals, 2y plus 3b. And then, okay, how do we represent things in terms of b, right? So you move the terms around, right? So 2y equals 3x. So then 2y equals 3x, move the 3x to the other side. So it's now 2y minus 3x equal 2b, I think I said, and then divide by 2. And so now b is in terms of the other things. Unfortunately, I don't have my my little whiteboard here. So, but it's basically rearranging of terms in an algebraic sense. And basically, just by doing that, some serious intuition that they had mathematically, they were able to rewrite something that, a loss function that had the reward model in there. They were able to find that the reward model can be written entirely in terms of the policy. And then they did a replacement, basically, where now the loss function inside of it, wherever you had rewards, those rewards were taken out and replaced by the equivalent terminology or equation, which was written entirely in terms of the policy. So you no longer needed a reward in there, and all you needed was the policy, which is the GPT. And so that effectively says this loss function just needs to optimize something related to one neural network and not the other, the GPT. So basically, through mathematical intuition, the reward model is incorporated into the loss function used to optimize the policy network. As previously stated, in RLHF, we need a policy network and a reward network. The policy network can be fine-tuned via human preferences. So we are talking about RLHF. The policy network should learn to produce results similar to human action. So that's what I was saying about, given a question and an answer, the human will say, okay, this answer is better than the other. So that's what this means. So the idea is, we create, given an input, a prompt, we're going to get two answers. So these results, these two pairs are presented to the reviewer, the humans for review, and the labelers indicate which produced action is better. And this is usually denoted as Y being the answer, W is greater than Y, L. So basically one is better than the other. I would give this one a higher score than the other one, for instance. So this has been modeled. So basically the whole the starting point of this is to think, okay, how do you model something like this process of somebody looking at this one and that one, given some prompt and saying this one is better than the other? Is there an equation that can help us, or a model that can help us to concretize this? And there is one, right? So there's a model called the Bradley-Terry BT model. So the human preferences, this is called the human preferences model, basically. So the human preferences can be learned by a reward model, and the corresponding distribution can be formulated as follows. So the Bradley-Terry model stipulates a formulation for the human preferences distribution. And that's this equation over here. So this is the first equation of this whole process. And you can see in terms of the policy, P, when you see a star, it just means that's the policy that you're trying to discover. Also, the reward here with a star also means that it's, something that we need to learn. But basically, it's saying, a policy that given X, what is the probability that one Y will be greater than the other? Well, that can be formulated as this equation, which is in terms of rewards. If you notice, reward in the numerator and rewards in here in the denominator and here in the denominator. Now, what's important about these is the reward has to be learned, but if you notice, it's given an X, so in this case, given a prompt, okay? And it produces an output, right? So one is, notice that the syntax changes a little bit here from W to L from W and L to 1 and 2, but it's the same thing. So here you have Y1, that's one output, and then you have Y2, another output. So basically you add these two, the reward of both of these, and then basically you have a fraction here that the numerator, so the probability of Y1 basically divided by the probability of Y1 plus Y2. And that's the Bradley-Terry formulation. And given this as their starting point, you're able to derive everything else in the normal process, right? So this is the normal process before DPO, right? So this is how it's formulated. So they basically then say, okay, based on this, with the rewards, let's figure out how this is done, okay? And so basically, you need to have this formulation is actually used to figure out what the loss functions will be to be able to train, a policy, which is really a GPT, to be able to provide good answers or better answers. So based on the previous formulation, the parameters of the reward model can be learned via maximum likelihood. So now the key thing is to express this as a loss function, correct loss function. So the objective can be expressed here as a binary classification loss, and this loss can be expressed as follows. You can see here, J denotes the loss, and really it implies it's in terms of the reward, an optimization. And if you notice, that looks at, given a prompt, the output YW versus given the same prompt, the output YL, right? So that's the formulation of the loss function to train the reward model, the second network. Once the reward model is trained, we can use it in the next RL phase to train the policy network, the GPT model, via the following objective function. And this objective function is basically you've trained the reward model, right? And now you just want to optimize the rewards, basically, think of it as maximize the reward that you're getting. So you're maximizing these parameters. So given a prompt, the very best answer that you can get. So you want to optimize that. Notice there is this parameter minus this expression here, right? And this expression here is usually referred to as the KL constrained objective. KL stands for the Kullback-Leibler. It's from information theory. It's basically so that you have two distributions and you kind of want, to measure how different they are. So in this case, you have basically, you use the KL divergence to keep the distribution from changing too much. So what I mean by that is that notice here that there's this pi theta and pi ref. So what pi theta and pi ref are basically here, they represent the GPT. So what you do when you start to train these things is that you have two GPTs. You have one GPT, which would be this pi theta GPT. That's the one that you're training. But you also have a pi theta ref. And pi theta ref is the same initially. They're basically the same one. So you create two variables with the same GPT in them. So ref just means like the untrained, unfine-tuned GPT. And then you're going to fine tune this one. But what you want to do is you don't want to let one GPT, the new GPT, pi theta GPT, you don't want to let it become too different from pi ref because, you know, you don't want it to diverge too much. So that's what the Kale divergence is. It's like you have a GPT that, you know, this is just an example, but can already write Shakespeare. You just want it to write better Shakespeare. So you don't want to modify this model so much that it no longer knows how to write Shakespeare, right? So by constraining it to this ref, it can always write Shakespeare, and then you just stay with improving it through this process. So anyway, this is the classic formulation. So far, this is, you know, how this would be done, PPO or some other technique. You know, this is the overall idea of or formulation that you want to do. Now, obviously, the problem here is that we're trying to optimize a policy, as you can see, but the policy depends on the reward and everything. So we need the two neural networks. What needs to happen, or what the authors of the DPO paper concluded very impressively, I should say, is that they basically want to write this whole equation, which is really the one that matters the most, in terms of policy, no rewards. So that basically effectively says, you know what, we don't need a reward neural network even. We don't need to worry about weights for that. We just worry about the weights of the GPT because we're going to create this amazing loss function for that. So the main innovation is that DPO leverages its choice in the reward model parameterization. So it wants to basically, you know, it's like a rewriting of the math, honestly. It's like they did a proof and they figured out, you know, this can be rewritten, and some terms, when they were rewritten, canceled out, and boom, they had a better equation. So this is kind of what I'm going to, the most important points that I will mention here. So they want something that simplifies the problem. Their key insight is to use analytical mapping from the reward function to the policy. So basically, what they've done is wherever they had a reward value, right? Wherever they had a reward value in the equation, they're like, okay, can we just change that to an equivalent written all in terms of the policy, the GPT? If you can do that and replace it in the function, then you no longer have to calculate rewards. You just do things in terms of the policy. So their key insight is to use analytical mapping from the reward function to the policy. So replace rewards with, you know, an equivalent in terms of policy or GPT. So this allows for the integration of the reward loss basically into the policy loss. That's why they had their clever name. Your language model is secretly a reward model. So you know, basically they're adding that in there. So this allows for the integration of the reward loss into the policy. As such, the policy model implicitly now includes the reward model, basically. In the DPO paper, the authors showed that the previous KL constraint reward maximization, all of this, maximization objective can be expressed in its optimal form solution, right? So I encourage you to look at the paper for the full-on proof of this, but they basically rewrote it as follows. So if you notice here, they rewrote the policy, the policy R in terms of the policy here. You know, they rewrote the terms, rearranged them. And here you can see the reward is expressed here. They have the C term, which is, you know, it's a complex equation as well. But this C term is called the partition function. and must also be calculated. And so this is something that was well known before, this formulation of the policy. And so because of this C term and because the reward is still there, this solution of the objective function was not practical in use. So this is something that, you know, it's like they had done this before and it just wasn't practical to do. However, this is where the analytical insight came that created the DPO method, right? So by just, you know, again, the author showed that the previous KL constrained reward maximization objective can be expressed as follows in its optimal solution form. So once they do this, they know this expression, still written in terms of rewards and policies. But this is where, so going back to the story, this is where their analytical insight came that created the DPO method. The previous formula, right, can be rewritten as follows, where the reward function can now be computed entirely from the policy in CX. And that's the key thing. So it's like you take this equation here, where you have a policy here, a C function here, a policy ref here, and then you have a reward here, you know, mixed in terms. You can rewrite it as this equation here. And if you notice, this equation is rewritten where a reward can now be computed entirely from the policy and the CX. So what that means is on the left side here of the equal sign, you have rewards. And on the right side here, notice you've got policy, and this CX function, okay? Even if that CX function, which is, I excluded that from this write-up because at the end of the day, this term actually cancels out. So even if it had rewards in it, you know, it ended up that when they plugged in everything, it canceled out. So that's the great thing. So with this insight and several conditions further discussed in the original paper, it was proven that the reward model used in the previously described Bradley-Terry model can be expressed entirely, can be expressed in terms of the previous equality. So that's really what they're going to do now, is that they're going to plug this in, right, into the original Terry model over here, okay? So I'll repeat this part. So with this insight and several conditions discussed in the original paper, it was proven that the reward model used in the previously described Bradley-Terry model can be expressed in terms of the previous equality. Additional, the intractable term CX cancels out. And so that's, you know, very good. After further simplification, the Bradley-Terry model can now be expressed entirely in terms of a policy, and a reward model is no longer needed. So that's the beauty of it. So if anything, just to kind of recap here, because we're almost done, you know, the initial Bradley-Terry model of the probabilistic distribution of one output being better than the other was in terms of rewards, if you notice. But we're training, you know, we're not training rewards just for the fun of it. We're training rewards so we can train policies or GPTs. So we needed both. But now they've taken this exact same equation, since they found that they derived basically that they could express rewards in terms entirely in terms of policies where this CX term canceled out, then now you have a way that you can take this RXY, sorry, that is here, RXY, and just replace these RXYs. You know, sorry, I'm not great with this. RXYs, these three RXYs basically with this equality, so which is entirely written in terms of policies and the CX term, which cancels out. So after further simplification, the Bradley-Terry model looks like this. So if you notice this model that was here, that is this one. Now this fraction here, this, you know, numerator divided by the denominator expression is now this one here. This one. And if you notice, if you compare the two, you will notice that inside you just have policy divided by policy policy divided by policy. Notice that the difference is here's y2, y2, here is y1, y1. So the two preferences. So this whole thing, which was written in terms of rewards over here, is now written in terms of policies. And that's the amazing, okay. Sorry, this equation 18. There you go, equation 18. So this is entirely like the insight, the mathematical insight. And once you have this, just like before, they started with this and derive this optimization objective number 15. Now, from this formulation, number 18, they can proceed and derive the loss function. So as from here, the new loss can be formulated entirely in terms of policies without the need for the reward model. And that's it. That's, the amazing insight. This means the policy network can be trained, the GPT, without the need of a separate reward model. And that is the amazing thing. So if you notice now this loss function, which initially was the loss function 15 with a reward in there, now has no reward in it. This is policy, GPT, ref GPT, policy, policy. For the given preference, notice is YW, YW, or YL, YL. And that's it. So this is the amazing thing about DPO, having two networks and now throwing out one and just being able to train on this one alone. So just these weights, not two sets of weights. So anyway, I read this paper recently. Took me a while to understand it, understand this basically. So I wanted to go over this idea. Yeah, so hopefully that's insightful to anyone that wants to understand what is the underlying math or intuition behind DPO, direct preference optimization. Okay. All right. So I hope this was helpful, and I will say goodbye here. Thank you.